Vacuum forming uses sheets of thermoplastic. The plastic sheet is clamped in a frame, then softened by heating. Then a vacuum draws the sheet onto the mould. Vacuum forming is a very cost-effective method of producing three-dimensional shapes, such as display items, refrigerated door liners, film sets, etc.
Hanging or hinging of various components, door bins, etc. And then filmed and cut to size, the gas gets added, and then there's the final prototype.
This is a roll-fed vacuum forming machine for high-volume production. An air blast pushes the finished item out of the mould. Moulds can be made in wood, or sintered, or cast aluminium, depending on production volume and details required. This is a wooden prototype pattern. It was used for test forming to check the dimensions of the item to be produced. After testing, a more durable and expensive aluminium pattern can be made. Vacuum is applied through the small holes in the pattern.
That's very typical of the interior of these models. You see all the vacuum ports around the various area there, the holes. And the rubber seal, which normally fits on this area, is used to seal it so that any material, or when the vacuum is created, it draws the plastic over the mould quite tightly. Let's extract it out. And that then produces the shape. You create different moulds depending on which surface you want to create. Female or male moulds. This one we require better interior detail, so we use a male mould, whereas this one we wanted the face detail, so we use a female mould for that one.
When made of aluminium, the pattern may be water-cooled to set the plastic more quickly and speed up production. Once a part is made, it's trimmed by a computer numerically controlled cutting head. The cutting head runs off the same drawing that produced the pattern in the first place. It can also produce any holes or cuts needed in the design. Two plastic sheets are cleaned and clamped into metal frames. Then the frames are moved under a heater. When the sheets are softened at 150 degrees Celsius, the frames are moved back to between the top and bottom moulds. A vacuum in each draws the plastic into the moulds. The moulds are then brought together and clamped, fusing the joints between the sheets. Compressed air in the cavity helps push the sheets more accurately into details in the moulds. The lid of this large container is vacuum formed. As only limited numbers are required, vacuum forming is the most cost-effective process. However, the container, produced in high volumes, is injection moulded. The mould cost of over $1 million was thus justified. This is an injection moulding machine. It injects molten plastic into a pair of steel moulds. A mixture of neutral and coloured plastic pellets is the raw material that's drawn into the moulding machine by vacuum. It is surprising how few coloured pellets are needed to produce the intense blue colour of the base of the box. This material is termed a thermoplastic, meaning it becomes soft or plastic when heated. A thermoplastic is easy to recycle because it can be ground up into powder and remelted any number of times. If it's coloured, it will be used with black. A thermoset plastic cannot be recycled because the heat sets it irreversibly. A complete injection mould is made up of two basic parts, referred to as the force and the cavity. The air gap between them is filled with plastic. Both parts of the mould are brought together with hydraulic pressure. The dies are water-cooled, so the plastic solidifies more quickly. The faster this happens, the shorter the cycle time, allowing more products to be made per hour. The moulds or dies for this box and its matching lid cost $50,000. The machine on which they were moulded about $200,000. So the faster products are produced, the faster the equipment will be paid for, and the cheaper the products will be. Expensive dies and high production rates mean that injection moulding is most economic with large numbers. It is far too expensive for small runs. Some items are moulded with a cold sprue when the appearance of a surface is not important, as on the bottom of this refrigerator crisper box. A sprue is the remnant of the feeder line full of plastic. It is cut off and later recycled. With time, the edges of the dies wear down and some plastic leaks. The flash, as it is called, needs to be trimmed by hand.
Okay, here's the two parts, the lid and the base.
The design challenge was to make a box with a hinged lid and a snap closure.
And you have the two undercuts there which clip together, and there's your box.
This detail requires an undercut in the tool. This can only be obtained by using a sliding core. This is an expensive addition to the tool. This slot engages with a matching protrusion on the edge of the box. These cores need to slide in when the mould closes and slide out when it opens.
Okay, these pins are angle pins, so they mechanically operate the sliding cores over here. So when the die closes, they'll push it, and then the locks will do the final lock, and they both push together. This one's a little bit different, it's a deeper cavity. We have what we call an air valve, which during cycle time it releases air, it releases the vacuum so it doesn't suck on and stay there. And there's these what we call interlocks. If these weren't here, then the die could shift ever so slightly and make a thicker wall section.
Where appearance is important, a hot sprue is used, as it allows minimum disturbance to the surface. The feeder line in the die is heated electrically to keep the material plastic, which then breaks off when the part is ejected from the die. This way, the injection point is very small and fits inside a dimple. It is an expensive addition to the tool, but can be justified if the appearance of the product demands it. The surface finish of a moulded component depends on the surface finish of the mould. This has always been done by hand. This hard steel mould required more than 60 man-hours to polish. It is an expensive process. Rotational moulding is most cost-effective for large hollow objects made in small runs. Manufacturing this buoy is a challenge. It is hollow and must be watertight. The only realistic way to make it is rotational moulding. Thermoplastic powder is poured into a mould. The idea is that the mould will be heated and the plastic powder will coat the inside surfaces. The moulds don't have to withstand pressure, so they can be made from sheet steel or cast in aluminium. They can be large because they cost only 5% of an injection mould. Also, for normal industrial products, the mould surfaces don't need to be polished. The moulds rotate on a 3-armed transporter. Here, there are 6 moulds, a pair on each shaft. While one set of moulds is unloaded and refilled with powder, another set is in the oven, and the third is being fan-cooled. When the moulds go into the oven, the plastic powder is melted to approximately 220 degrees Celsius. To coat all the inside surfaces evenly, the moulds are rotated in 2 planes. Here, the 2 moulds are mounted on each shaft for balance. Although this box was made hollow, the design is for a box with a lid. This computer numerically controlled cutter is using data from the original design and cuts the lid away, leaving supporting points on each side. The supporting points are later removed by hand. This canoe is double-skinned for strength and buoyancy. The mould is in 2 parts, one for the deck and cockpit, and another for the hull. The inside of each has a polished, mould-release coating to produce a good finish. First, the name label of the canoe is applied on the inside of the mould. Plastic will adhere to this and the name will eventually face outward. Next, steel tubes are inserted temporarily into the mould, so plastic will form around them. They will form hollow supporting columns inside the cavity. Unlike the injection moulding process, the coloured pellets are ground to a powder before use. The quantity of powder determines the wall thickness of the finished product. A thicker wall using more material would be stronger, but heavier and more expensive. The mould is closed and clamped in place. Being pivoted on its long axis makes it easier to get to the top or bottom during mould preparation. Some areas of the canoe mould have details that require additional preheating to make sure that the plastic powder coats these surfaces appropriately. The handheld thermometer measures the temperature of the preheated areas. The whole steel frame assembly is on wheels, which runs on rails into the oven. The electric motors on the frame rotate the mould on its long axis, as well as providing a seesaw action to spread the plastic powder evenly. The cycle time for the canoe is about 30 minutes. It must keep turning during the cooling stage until all the plastic is solid. The steel tubes are removed with a few blows on a plastic drift. The resulting columns also act as drain holes. Edge flash is trimmed where the mould parts joined. The finished moulding is flame polished to remove any slight defects on the surface. Although rotational moulding is slow and labour intensive, the tooling cost is 1/5 of that for injection moulding. The casing for the ambulance kit is an excellent example of what can be made by rotational moulding. It is assembled from 4 components made in 4 moulds. Each lid is hinged on a pin moulded into the body. The walls are hollow and have been filled with foam to provide insulation and impact resistance. If it was made in large numbers, it may be more economic to use injection moulding. The design, however, would need to be different. Blow moulding is used mainly for making plastic bottles and containers. Molten plastic is extruded as a tube crimped at the bottom. When the mould closes, it crimps the tube at its edges. Compressed air then blows it into the shape of the mould. Each container is tested for leaks. Here, the operator proves the accuracy of the test by putting a hole in a bottle. Blow moulding is the only cost-effective way of making a thin-walled bottle. Rotational moulding would be too slow and the walls would be too thick.